kinetic and thermodynamic products in the nucleophilic addition of alpha-beta unsaturated aldehydes and ketones. When you have two competing reactions, and if both the reactions are irreversible, like what you see in this case, direct addition and conjugate addition, in that case, the reaction will be kinetically controlled, which means the product that is formed faster is going to be the major product. Let's say you have a nucleophile, which is a strong base. This nucleophile will go and immediately attack the carbonyl carbon, thrust these electrons onto oxygen. So in that case, it's going to form a tetrahedral intermediate. And because this nucleophile is a strong base, it's not ready to leave from the system. And therefore, the direct addition product will be formed. Grignard reagent and hydride ions are examples for stronger bases. Let's say that your nucleophile is a weaker base now. The weaker base will still be going and attacking this carbonyl carbon, thrust these electrons onto oxygen to form the tetrahedral intermediate. Now, because your nucleophile is now a weaker base, it's ready to leave from the system, because we know that weaker bases are better leaving group, right? So it's going to leave from the system, and therefore the tetrahedral intermediate is going to collapse. But when it collapses, it's going to form the starting material back. This starting material has got a second chance where the weak base will go and attack this electrophilic site, and it will give us the conjugate addition product. Well, this is the stable product that is formed. This one right here, the product from the direct addition is going to be the fastest product. But since you have at least one reaction which is irreversible, the reaction would be thermodynamically controlled, which means the most stable product would be the major product. Some examples for weaker bases include halide ion, Cl-, Cn-, or thiols, or alcohols, or amines. These are some examples for weaker bases. All of these right here, cyanide ion, halide ion, thiol, and amines are weak bases, and therefore you can only see conjugate addition product. And where the nucleophile goes and attacks the beta carbon. So here are beta carbons. So this one, this one, this one, and this one are our beta carbons. And this is where the nucleophile is going to go and attack. Now that we know how the nucleophile is going to affect the two competitive reactions, let's now focus on the nature of the substrate, basically the nature of the alpha-beta unsaturated carbonyl compound. Now, we have talked earlier about the reactivity of aldehydes and ketones. Aldehydes are in general more reactive than ketones, right? So which means it's going to have a greater partial positive charge on this electrophilic carbon than what does a ketone have, right? So this carbon right here in aldehyde, it is more electrophilic than what you see in the case of ketone. And therefore, in the case of aldehydes, you'll get more of the direct addition product, which is the 1,2 product. Whereas in the case of ketones, it would be a mixture of 1,2 addition and 1,4 addition. 1,2 plus 1,4. Let's take a look into this reaction. So here we have a ketone, alpha-beta unsaturated ketone. Here is a functional group, and this is being reacted with sodium borohydride, which means you are having a hydride ion as the base. So which is a strong base. The strong base, although we have a strong base here, it's going to do both 1,2 addition and 1,4 addition because the ketone is less reactive than aldehyde. So let's write down the two products. This one right here is the product of 1,2 addition, because you can see that the double bond has been preserved. And this one right here is the product of 1,4 addition. This one is basically the keto tautomer of the enol that is formed in the conjugate addition. Here, the hydrogens which are in blue, which are highlighted in blue, are basically the hydride ions which are added to the carbonyl compound. So here in the 1,2 addition, the hydride ion was added here as a nucleophile, right? And that's what we see here. And in the case of 1,4 addition, the hydride ion was added to this carbon, which first forms the enol, and then the enol will undergo keto-enol tautomerization to give the keto form. And here are the ratios for the two different compounds. And as you can see from here, both of these two compounds are formed with equal ease. Let's take the case of aldehyde, alpha-beta unsaturated aldehyde. So this is our functional group, aldehyde. And again, you're reacting with a strong base. So here in this case, there is going to be 97% of 1,2 addition product. And the only reason for this is the cardinal carbon is more reactive here. And therefore, the direct addition occurs predominantly. There is also a second factor with respect to the substrate that's going to affect the product distribution in these two competitive reactions. And that is steric hindrance. Steric hindrance generally favor conjugate addition. Now, why conjugate addition? Let's take a look into the structure of aldehydes and ketones. We have talked earlier that the aldehydes are more reactive than ketones. This is because of two reasons. First is the aldehyde has got more electropositive charge on this electrophilic carbon, right, compared to ketone, and therefore the aldehydes are more reactive. And the second reason is that the aldehydes are going to have less steric hindrance. Say, for example, when you take a look into the structure of aldehyde, you only have one hydrogen on one side of the carbonyl group. But here in this case, in ketones, you have substitution on both the sides of the carbonyl group. And because of which there is greater steric hindrance here in ketone. And because ketones have greater steric hindrance, it will be difficult for the nucleophile to approach this electrophilic carbon, right? And because of which you can expect ketones to form 1,4 addition product, where the nucleophile, which is C6H5 minus, should be added on the beta carbon. So this one right here is the beta carbon, and the nucleophile has been added there. But in the case of aldehyde, it should be a direct addition where the two groups are added at the 1 and 2 position. So the nucleophile here is CH3 minus. It's been added to this carbon, and the hydrogen is getting added here. So in aldehydes, the reason why 1,2 addition predominates is because of their high reactivity and also less steric hindrance. When it comes to organocuprates, they only form conjugate addition products. Now, why? What is the reason for it? So we have talked earlier that Grignard reagents is going to lead to the formation of direct addition products. Why? Because it has a strong base, which acts as a strong nucleophile, right? So in the case of Grignard reagent, we said that it's going to be a strong base. So this part right here is a strong base. But if you take a look into organocuprates, organocuprates also have an alkyl group attached to the metal. So we may be thinking that this should also behave as a strong base, but this is not the case because the carbon metal bond is less polarized here. And because of which, it's not able to go directly attack the cardinal carbon. Instead, it will go and attack the beta carbon and finally form the 1,4 addition product. When nucleophile reacts with alpha-beta unsaturated carboxylic acid derivatives, it has got two options. One is to undergo nucleophilic addition elimination reaction, and the other one is to undergo conjugate addition. But which of these will be favored? It's going to depend on the reactivity of the carboxylic acid derivatives. Here is the relative reactivity of different carboxylic acid derivatives. You can see that the acid chlorides are more reactive than aldehydes. And then you have ketones, and then carboxylic acids and the esters are going to have about the same reactivity. And then finally the amides. The amides are the ones which are least reactive. So when you're going to react an acid chloride with a nucleophile, it's going to do the direct addition, but the direct addition will be converted into a nucleophilic addition elimination reaction since you have a leaving group here. So it's still going to form the tetrahedral intermediate, but because you do have a leaving group, that it's going to leave from the system and it's going to give us the nucleophilic addition elimination product. So this one right here is a nucleophilic addition elimination product. But whenever the nucleophile reacts with the carboxylic acid derivative, which is less reactive, say for example in the case of amide or in the case of esters, it's going to give us a conjugate addition product. So all of these are conjugate addition products. And in the conjugate addition product, obviously the nucleophile is going to attack the beta carbon. So here is our beta carbon. So all of these will be attacked to give us a conjugate addition product.